Hey guys, my name is Adrienne and welcome to Organic Chemistry 2, Part 2 of these recorded sessions. So today we'll be going over for most of y'all Chapter 14 and in general NMRs, so Nuclear Magnetic Resonance Spectroscopy, right? So once again, if you haven't seen the first video, the format is a little bit different um, from the OChem 1 videos we used to watch and make, right? I decided to do a split screen for the first half of the video, kind of just like the board and the review questions. So I'll be doing review questions with you. You can stop and pause and take screenshots, do them with me. Scroll if you just want the questions and don't want my explanations. But if you do get stuck, feel free to come back on the recorded videos and see the explanation, things like that. So the reason why I did that is because OChem 2 is more practice based, not necessarily concept. So, and a lot of graphs, a lot of reactions, a lot of drawings, more intensive drawings. So, this is kind of the best way to kind of for you guys to see the format, better format, and just get familiarized with it, right? So, hopefully, you guys prefer it. It makes it smoother, I feel like. Um, based off the first video because and also it makes it shorter, kind of faster, more guided and um, less messy, right? So yeah. So with that being said, let's get started with our reviews. So and again, at the end we'll have a summary page. So we'll go over some main points and obviously about the chapter, right? About the title, NMRs. So if you want to skip to that part first, then come back with and do the questions. Feel free, experiment, do what you want. You know, do what your study preferences, right? Okay, so with that being said, let's get started with the questions. So again, first things first, pause the video, attempt or screenshot or, take notes or whatever, and come back and we'll compare answers, right? So one, you should have gone D. And why D? So since this is the first question about H and MR, right? Let's do them all. And then from there, we'll kind of just, kind of eyeball it, things like that, do it if really, we're really stuck, right? So let's do the whole thing for this one. We have this one. We have this one. And we have this one. Okay. So for the first one, where are all these hydrogens? So unique protons, right? So pretty much proton environments, hydrogen environments, whatever you wanna call them, but they have to be unique. And we know that in straight chains, as long as they're in each carbon, they're pretty much all different because their um, their environments are different, right? This carbon is closer to this double bond than this carbon, right? So even though they are all CHs, right? So in this case, these are the hydrogens, and I'm just going to number them, right? So we have one here, one environment, two, three, four, and this is the fun part, right? It's double bond. Double bonds don't spin, so both those hydrogens are stuck there. So that means they'll have different environments as well. 5 and 6. And you kind of can tell by if you cut it in half, right? If you cut it in half, this hydrogen is closer to this group, while this 5 is closer to 4, right? So cis versus trans, that type of thing. So now for the second one, these two environments are the same, right? So 1, 2, 3, and of course the OH 4, right? So far so good, 6, 4. And now for the third one. The third one is always the one that gets students because it's kind of tricky. It's kind of not fair. So this is where we get them. 1, 2, 3, 4, 5, 6, right? So now you're wondering about these. Why are both of these different, right? Why are all of them different? Well, to kind of point that out, to kind of explain that, it's because this over here is a chiral center. So four different groups, right? So thinking back to OChem 1, chiral centers, four different groups, right? So just imagine it, four different groups spinning, right? So it's spinning, they're all single bonds over here. So at each point, at each time, at every angle, since there are four different groups, right? At every angle they spin, they're different environments because this hydrogen will be right next to a different group, while this hydrogen is right next to a different group, right? So no matter how much they spin 360, they're all experiencing different activities. And another thing with this is that depending on how many chiral centers, it affects, um, you know, it doesn't affect the whole chain. It only affects this adjacent carbon, right? And then this next carbon. So it can only go up to that point. So it's not gonna, if you have a longer chain, it's not gonna affect all of it, right? Because the effect isn't that strong, but the environments are still there. So that type of thing. So it's a kind of a little tricky because again, chiral centers. So watch out for chiral centers. You're not gonna see them often, but chiral centers are one of those things that are easy to kind of pick out because four different environments or four different groups. Chiral center straight away. So think about chiral centers, but most of the time you won't have to because hopefully your professors aren't that mean, right? So just depending on that. So maybe ask them. Okay, so 2, you guys should have gotten B. And again, why B, right? So let's do this whole. And we know how to get our splitting, right? So this is asking about peaks, so splitting patterns of the hydrogens circled. So since we won't have room, let me do the tricky ones. I'll do one of these kinds, and let's do let's do this one, the third one, BR, and then let's do the last one, H3. And this is also a good question because this is where students kind of forget one important rule. So this is what we're looking at, and we know environments are affected by adjacent carbons, right? So it's affected by these splitting patterns, right? So we have hydrogens over here, hydrogens over here. So are these hydrogen environments the same? No, right? So these are, let's call this one, let's call this 2, right? So they're different. So what do we do? How do we split this if both of these are different? We think about our n plus 1, m plus 1 formula, right? So 2 hydrogens plus 1 times 2 hydrogens plus 1, again, right, equals 9. So that's how we get the 9 splitting pattern, right? So that's how we do that. And you only use this when adjacent carbons are different, right? When adjacent carbons are different, we use this formula. If it's not, we just use n plus 1, right? So now, for example, over here, this only has one adjacent, right? This H over here. So this one is only going to be what? And this is the third one. So it's just going to be n plus 1 because it only has one adjacent carbon, right? So, and it's one hydrogen plus 1 equals 2, right? And now this one, oh, this one is this H over here. And how many adjacent carbons? So this is kind of tricky to kind of visualize it. So this is the carbon it's attached to, right? The H is attached to. So the adjacent carbons are this one or this one. This one has 3 attached to it. This one has none. So it only has, again, one environment attached to it, right? So we use our n plus 1. We have 3 hydrogens plus 1 equals 4. So it splits into 4, right? So nothing too crazy. You apply the same thing to that. The most important takeaway from this question is this n plus 1, n plus 1, right? Don't forget about that because if you don't do that, you'll get the wrong answer, right? There's just no way you can get the right answer from using n plus 1 from this because if you use n plus 1 only, you'll get what? 5. You're 4 off, right? So don't forget about this. Okay, now 3, you guys should have gone C, right? And this one, same thing as 1. How many protons are there? So let's see. So same thing. These are all the same, right? 1, 1, 1, 1, 1, 1, 2, 3, and 4. 4. So, and then we should be down to B, C, and D, and then so on and so forth. So 2 we can get, 3 we can get, 4 is the same as 1A, right? Or yeah, 1, number 1, um, option 1, I guess. The interesting one is this one, right? This is probably the more kind of mixed up one, because how do we find out, how do we visualize the different environments in these? So since obviously they're wanting you to do trans cis, right? The best thing to do is kind of draw it flat, right? So now it's flat. So now we'll do this 1, 2, 3. So 3, 1, 2. So that's kind of a reference. So 1, we have a methyl group going up. 2, we have a methyl group going down. And obviously these have hydrogens, right? So hydrogens, hydrogens, hydrogens. Same thing over here. Hydrogens, 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 right? So over here, up, we have a hydrogen, right? Down, we have a hydrogen. And same thing on these carbons. And I'm going to slant them a bit so we can see so they're not like, so up, we have a hydrogen over here. And then down, we have a hydrogen down there, right? So you kind of see where it's falling now, right? So here, these hydrogens, 1, right, are the same as these hydrogens down here, right? And then now, these 2 hydrogens are the same, and these 2 are the same as well. And you do this because think you can even just look at the top part, right, and see that this is different from um, this one, right, and then vice versa. So things like that. So um, That's where you get the 1, 2, and 3. And actually, hopefully some of you guys caught me. Um, these these top ones are actually the same. So sorry about that. So and the bottom ones are the same. So this is H3, H3. So these two are the same because they're getting affected by this, right? And then these are getting affected by the threes. This is the same as this one because they're getting affected by the two hydrogens over here, right? So, okay, I hope that makes more sense. And then these are our coordinates, right, over here. So, yeah, hopefully that makes sense. So just lay it flat and, you know, add those hydrogens in. And we know there's hydrogens there because they're just invisible, right? Because they're skeletal structures, but just add those in and you should be good. And kind of just visualize which one is close to what and count from there, right? Okay, so let me erase this since we're totally out of um, room. And then for 4, you guys should have gone D. And this one is also about peaks, so similar to number 2, but now you can kind of see different types of ways of asking these, right? But now it's asking about, it's asking it in compressed formula, right? So we have this first one, BR2, or BRH2C, C, H, and that's the one we're looking at, CH2BR, CH2BR. Okay, so this one's an interesting one, because what do you notice? Right, these environments are all the same, right? These H's are all the same, 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 same. So what do we use? N plus 1. So there's 2, 4, 6, 1 equals 7, right? So these are all the same environment. So pretty much it'll look like this. This is what it should have looked like. H, BR, BR, BR. That's what it looked like. And all of these are all the same, right? So, okay, let's do the next one. Um, if we drew the next one, it would look something like this. OH, and then let's see, one over here, then this is the H, right? And then we're looking for this one. So this one you split it, what? Again, we just look at the adjacent, right? So adjacent over here. So you should have gone just n plus 1 again, because there's only one adjacent carbon, right? And then it's just 1 plus 1 and 2. And we don't count OH, right? Because any hydrogens attached to an O doesn't count. We don't care about it, right? It's just by itself. It's just 1. But we don't count it as an environment. It doesn't split the adjacent hydrogens, right? Okay, so the third one, if we were to, again, if we were to make it into skeletal structure, it's what? 1, 2, 3, 4, 4. Okay, then we're looking for this H, pretty much. H, H. Okay, so now what do you do? So, for this one, why did we only get 3? Well, this case, it's symmetrical, right? So these are the same environment. So we're not going to count each other for the n plus 1 or the splitting, right? So we're only going to count these over here, right? And these have 2 hydrogens. So n plus 1, 2 plus 1 equals 3. See? because these are the same, we don't count them into splitting because they don't. If they're the same environment, they don't split each other, right? Um, that's all there is to it. So pay attention to symmetry as well. It's kind of like a good, and pretty much if it's symmetrical, obviously you just count one half, right? So pretty much you could have just looked at it like this, right? This molecule by itself and still would have gotten the same answer, 3, right? So symmetry is good too. Okay, so that's that for the first page. That was kind of a lot of drawing. See, I wouldn't have been able to fit all of this in one page if I just wrote it down, right? Like in OChem 1. And it would have been way too messy. So, okay. So, again, pause the video, make your notes, try to answer them, and come back with an answer. Okay, you're back. 5, you guys should have gotten A. And why A? Again, a lot of asking for protons, and um, it's important to know where these protons go and what they represent and stuff, because reactions. This is important. Reactions, which again, kind of very repetitive, right? We care about what leaves, where they attack, things like that. So we want to know what these hydrogens are capable of, right? So hydrogens are very important. Okay, so the first one, um, very easy to see, right? So, and I wish I could write on the thing, but I can't. I can only write on the board. I wish I can write on the actual page, but so I don't have to like rewrite everything, right? So again, we have 1 right here, 2, 3, 4. So 4 environments, easy. Um, for the second one, we are C C C O C O H H H H. So we have just 1, 2, 3. 1, 2, 3, right? So not too bad. And this one, what do you guys think? So again, symmetry, right? So there's a good example of symmetry. Symmetry over here, symmetry over here. Um, any other ones? No, that's pretty much it, right? So pretty much we can omit all the other ones and just keep one corner because it's not gonna matter, right? So we can omit these parts, and now we just have these hydrogens, and they're the same environment, so just one, right? Boom. So there's just one environment because they're all the same, right? So that's how you do that. That's how you pull off the symmetry thing, right? Okay. So now 6. Let's see, 6. Again, how many different kinds of protons? So a lot of questions like that. I don't know if you guys are tired of that, but or if you need any more explanations. But 6, you guys should have gone B, and nothing fancy here. Again, a double bond, right? Um, this H is different from this H, right? So, and then other than that, um, 1, 2, and again, it's symmetrical as well. So actually, they're symmetrical. It's actually the same. 1. Oh, did I skip a question? I did. I was looking at 7. Okay, scratch that. 6. Okay, 1, 2, 3, 4. 1, 2, 3, 4. Like that, and then pretty much H is over here. So, well, I guess same thing, right? Double bond again. So, I wasn't completely wrong, right? Again, double bond, all of these H's, one, two, three, four, five, six, right? Double bonds can't rotate, so each substituent is different, pretty much, right? So, and then again, actually, let's do this one for six. Six, we said was B, so this one should have three, right? So we have a Cl going up, and then a Cl going up as well. And then obviously we have H going down, and then H going down over here, and then H up here, H up there. Okay, so hopefully, so this is our main one, right? Okay, so now which ones are the same? So if you look at it, kind of same thing what we did. These H's over here, right, are the same, right? So we'll label that one because they're both over here, and yeah, they're both experiencing the same thing, right? Because this hydrogen over here has hydrogen up here, has a hydrogen down here. This one is the same thing, hydrogen up here, hydrogen down here. Now these two are the same as well, right? And then these two are the same. So that's how we get that, right? These two up here on the H3s here are close to the Cls. H2s are trans from the Cls and cis to the H1s. H1s are trans from the H3s and cis to the H2s. So we kind of see like each different environment are close to something different, right? So kind of like how you visualize that as a cis and trans thing. Okay, so let's move on to seven. Seven, you should have gotten C, and this one is pretty simple, so I think we can skip it, right? Double bond. Two is three. They're all threes. Three has symmetry, so keep that in mind, I guess, right? So yeah, they're all threes. So now let's go to eight. Now a different question finally, right? Which of the labeled protons absorbs furthest upfield? So you should gone B because we know upfield is where? Upfield and then down. Upfield means what? Shielded and de-shield, right? So that's kind of what you're looking for. So which one of these? It says upfield, so most shielded. And why do we think that? So 8 is, oh, actually, I was looking at the wrong question. I was looking at 9. Come on. Okay, so if you guys didn't think it was B, you're good. So 8 is D, because I was like, okay, farther upfield, more shielded, that means it's away from electronegative elements, right? So nothing it's taking is electron density away from it. So it's getting it close, like, okay, I feel protected because no one's trying to steal these away from me, right? No one's trying to steal my hydrogens away. So which one is the farthest from the more electronegative parts? D, right? HD. And the electronegative parts we're talking about is the aromatic, right? The resonance that makes it really electronegative, and the oxygen, right? So that's that. So actually, what would be the most D shielded? And this is a good question too, because Again, I always kind of encourage you guys to get these questions. You'll have plenty of practice questions for each chapter, right? So get these questions, rearrange them, ask different questions, do the opposite question type thing, right? So we could have asked for this downfield. We could ask for this question, rank them from most upfield to downfield type kind of thing, right? And even your professors will ask the same thing. Rank which one's the most shielded, rank them, right? Which one's the most de-shielded. Or instead of um, asking upfield, downfield, they can say de-shield, shielded, right? So interchangeable terms, things like that. So get used to that. That's what it's all about, right? And they're just fun terms too. Like you sound super smart saying it, right? Like simple words that mean totally something else. So that's good. Okay, 9. This is what was the right. So which of the indicated protons in the molecules below would absorb furthest downfield? So another type of question with dealing with upfield, downfield. So B, furthest downfield, because it's right next to that oxygen, right? So that hydrogen's right there, right? Very close compared to the other ones. One doesn't even have oxygen right next to the hydrogen they're pointing at. Same with 3 and 4. This is where kind of like the controversy type thing. So what's the difference between 2 and 4? Well, 2 has these groups too, right? Methyl groups. This one has hydrogens. So which do you think will pull more? The methyl groups or the hydrogens? Methyl groups, right? So that kind of thinking, pretty much anything's more electronegative than hydrogen, right? So that's that. Okay, so let's go to the next page. So again, pause, take a couple minutes, um, try it out, and and again, 11 is a good example of why again split screen is the best for OChem 2 because if I were to draw that, you guys wouldn't have a clue what I was trying to say. Okay, so anyways, 10, you guys should have gotten B. Okay, which indicated protons would absorb furthest downfield? So kind of, I think these are like, no, they're not. So kind of like the same, pretty much exact same question. Furthest downfield in an H&MR spectrum, B, right? So same reasons. Yeah, exact same reasons. So let's put here same as number 9. C number 9, right? Okay, 11. Compound X has a molecular formula of C8H10 and gives H&MR spectrum below. What is the structure? Okay, so this is where your charts get handy because you can see where um, each bond absorbs type thing. So 11, you guys should have gone something like, and this one's a good one too. You should have gone B because, right, what, where does aromatic absorb? So it absorbs about 7, right, 7 ppm. So now, over here, these H's are probably, since they're closer to the more electronegative aromatic, right? These are the ones probably around 3 area, right? And then these are probably the more shielded, which is the ones, right? And if we really want to risk it, for sure we can take out A and D because they're not aromatic, right? They're not in 7. And for C, you would have gone just threes, right? In the 3 because those H groups are close. And also you can kind of see how this one is what type of splitting pattern? 4, right? Quartet. And this one is a what? A triplet, right? While over here, these would have been what? These would have been singlet. And there's no singlet in that graph, right? This is the choice C. This is the choice B. Right? These are all singlets, and on our graph, there's no singlets on in the threes. So no three singlets is the best explanation, right? So that's why B is the best choice. Now 12, again with the peaks, right? And 12 is a good one, so this might need an explanation. H, oh, H3C, oh, C, CH3, 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 HH. So don't be fooled by this. Literally, it's just symmetrical, right? Symmetrical. So again, we don't care about this side. We don't care one of the sides. Um, oh, and you should have gone for this one, C, 7, because again, if we erase this part, or I guess let's erase this part because it's the more bulky one. So it's symmetrical, so we can ignore this side, right? And focus on here. And the adjacent carbons, where are they? And this is what we're talking about, this H, right? So the adjacent carbons are over here and over here. And they're the same environment, so n plus 1, and we have 6 hydrogens, so 6 plus 1 equals 7, right? So not too bad. Kind of a lot of different ways to ask this, and the only way that you'll get confused is because they kind of throw these steps at you like they're not skeletal structures. I prefer skeletal structures because, they're more simpler and less crowded, right? So, but that's all there is to it. There's symmetry. You're good. You just count one half of it. Okay. So now let's go to the next page. And this time, instead of HNMR, we're talking about CNMR, which is even easier, I feel like, because CNMR, no splitting, right? So I guess before I said that, pause the video, take your time, and come back when you have these ready. Okay, so 13, you guys should have gone B. And for CNMR, no splits, right? No splits, which is good, and we'll literally just count carbons directly. Unless they're symmetrical, we count all the carbons, right? So the first one has how many carbons? 1, 2, 3, 4, 5. We're good. The second one, 1, 2, 3, 4, 5, 6, 7. But this one is symmetrical, so B is actually symmetrical, right? It's symmetrical this way, so we have 1, 2, 3, 4. We actually have 4 only because it's symmetrical. C, we just count all the things because they're not symmetrical, so we just count all the carbons, 1, 2, 3, 4, 5, 6, 7. D is also symmetrical, so we can cut it in half, and 1, 2, 3, right? So that's it. We just count the carbons. And now, another way to kind of ask this question is instead of asking directly how many signals, how many peaks. So kind of the same thing with HNMR. But again, we just count the carbon for each of these. So we're looking for 6. So for 14, you guys should have gone, let's see, 14B, right? So, and B is symmetrical, right? So we have 1, 2, 3, 4, 5, 6, and the rest give more than that. I think 1, that's 6, 7, 8. 1 gives 8. 3 gives 7, and so on and so forth. So, no, 3 gives 5. Let's do 3. 1, 2, 3, 4. Yeah, this is 3, and this is 2. Right. Okay. So whatever, nothing too crazy. And now for 15, it's just one of those kind of terms. So 15, you guys should have gone A, homotopic, right? And Y, because they're literally the same hydrogen, right? It's symmetrical. They're mirror images pretty much. So HB, HA, right? They're symmetrical. So exactly the same. And if it was an anisotropic, going back to enantiomers, diastomers, right? It would have been flipped as well, like R and S, things like that. Mesotropic, yeah. And even then, none of these are chiral centers, right? So we can't even have enantiomers, diastomers, or mesocompounds, right? So not chiral, so we can't even have enantiomers or diastomers or mesocompounds. So that's another. See, chirality again. Chirality strikes again, right? Okay. Now 16 is probably the favorite. Not, I shouldn't say favorite, but kind of like the combination of chapters 13 and 14. So you kind of use all of them, but you kind of just go along with it and see what you need to use, which one you don't have to use. But it's a good review for all, especially if you're studying for the final, things like that. You just do one of these questions and you pretty much use all your knowledge about spectroscopy and you're good. Okay, 16, you should have gotten C. So why C, and how do we tackle this question? So, and I'm going to use a whole page for this. Okay, okay, so this is our first choice. Um, our second choice, and this is a good like overall type thing. So, first things first, what I do is obviously find how many environments there are. So the chart is telling us how many environments we have. We have 4 HNMR environments, right? Because they told us there's a triplet, a singlet, a quartet, a singlet. So 4 environments. So now I look for my 4 environments. So we have one here, 2, 3. So this one's already out, right? What about this one? 1, 2, 3, 4. So far so good. We have 4 environments. For this one, 1, 2, 3, 4 environments. That one's good. In this one, we have 1, 2, 3, 4 environments because this is symmetrical, right? So 4 environments. So we can cross out this one right away. So now what I do is look for the splitting pattern. So it says triplet, singlet, quartet, singlet. So this one here, OH, is automatically a singlet, right? Singlet. This one is gonna be a doublet, right? Because this adjacent one only has one hydrogen. Doublet. And do we have any doublets that they told us about? No, right? So no doublets. This one, singlet, because there's no adjacent carbons. This one, triplet. This one, um, you should have gone quartet, right? Quartet, because there's no hydrogens over here, only here. And this one, you should have gone triplet. Or I mean, yeah, triplet. triplet. Okay. Oh, actually, hopefully, did anybody catch this? This one, so these are methyl groups, right? The hydrogens are out here, so the adjacent is this carbon, and this carbon doesn't have any hydrogens, so this is actually a singlet. Do you guys catch that? Um, so the hydrogens are attached to this carbon, right? To these carbons. And the adjacent carbon is this one, which has no hydrogen. Um, so it has to be singlet, right? So, okay. So, yeah, so far so good. Everything's on there. And what about this one? We have triplet over here. This one. This one has two different environments on adjacent. So what do we use? N plus 1, M plus 1, right? So N plus 1, M plus 1, and we get what? Over here, 3 plus 1. Over here, 1 plus 1. So 4 times 2, 8. We don't have any 8, right? And you, from there, you kind of just keep going down. So let's say there was a tie, right? So this one has all the splitting patterns as well. Then now we'll go to the middle of the chart, the sigma, um, the ppms. So now we compare. Okay, it's there's a ppm in 3.5. So what bond is that? So that's kind of what we look for. So which ones of these are shielded, deshielded type thing, and we'll be doing that. I think the next question. So okay, let me erase this. So and then let's do another one. So 17 is a good one. Again, attempt it and see what you guys get, and let's see. Let's compare. Okay. 17, you guys should have gotten A. And why A? Again, let's do the same concept. Let's do a whole page for this one. Right? And this one you actually use everything, I think. Let's see. And hopefully this is making sense. And pretty much, go step by step. Don't be overwhelmed by the chart, right? Just go step by step, and you know how to do splitting patterns. You know how to find the environment, so no big deal, right? So again, it's telling us there's 4 environments, 4 HNMR environments. So let's look for 4. 1, 2, 3, 4. Right? There's no hydrogens over here, so we don't have that. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4, 5. This one has 5, so we can cut that one out, right? So now again, let's go to the um, splitting pattern. So we're looking for triplet, doublet, septet, quartet. So this one, triplet. This one, um, quartet. This one, septet, right? This one, these two, I mean, doublet. So far so good. This one over here is a doublet as well. This one is a septet. This one, quartet, and this one, triplet. So pretty much the same, right? So far so good for these two, or 1 and 2, 4. So let's look at this one. So this one, singlet. This one, again, is a singlet, right? No adjacent carbons that have hydrogens. So right away, we don't have 2 singlets. We don't even have singlet at all. So we can eliminate this one. So now, again, as I was saying, right, we came at a tie. So let's divide this. So now it's a tie. What do we look at next? Now we look at the ppm, which is the sigma, sigma notation there. The 1.2, 1.4, 1.9, 3.5. the ppms, right? So let's see here. The triplets are kind of in the same place, right? Triplet over here, triplets at the end, so that's not gonna make much of a difference. The quartet is right next to the O here. The quartet over here is right next to carbons. So it's saying the quartet is at 3.5. Is that shielded or de-shielded? It's gonna be de-shielded, right? 3.5 is like halfway down. Um, so we can safely say that that quartet is de-shielded. So if that quartet is de-shielded, which one of these quartets is it? This one, right? Because it's right next to the oxygen, so that's what's making it de-shielded. So that's why it's that. So this is 3.5, right? And you can even go, check all of them. Let's see. You can check the septet, right? The septet is saying 1.9. The septet over here is right next to O, so that's not going to be 1.9, right? But over here, the septet is over here is very shielded because it's just right next to carbons, right? So things like that, um, that's how you would use the ppm, right? Is this environment de-shielded or shielded? Where would it fall on the graph, right? So that's kind of how you do that. Hopefully that helped. And you do the same thing with all the other charts. You do the same thing if you're given multiple scenarios. So same thing. Okay. Now 18 is also kind of just like a concept one that's kind of like, okay, we get it, right? So 18, you should have gotten B, and that's just one of those things you get kind of need to know. Display speaks where only carbon that bear hydrogen atoms. Not true, right? CNMR is all carbons. It's just carbon environments everywhere. 19, you guys should have gone for this one, C. And this one's an interesting one as well because unknown formula C9H12 and doublet, and so this is kind of like a different version of the chart, right? So let's just do C. And this is a good one, a good example too, because it has three environments, right? So 1, 2, and this whole aromatic is 3. So we're counting that whole aromatic as 3, because it's just symmetrical on itself, right? And actually, that 3, that aromatic, is the one at 7.09, right? Because we said aromatics are 6 to 7, right? And then it's just aromatics appear as one big multiplet, right? So that's just something you need to know. Aromatics appear as one big multiplet. So 3 is also that multiplet, right? So don't forget that. Aromatics see as multiplet. And then we have a doublet. And where is that doublet at? Doublet is the ones, and then 2 is the septet, right? So it meets all the criteria. So that's why it's C. Okay. 20, you should get C, which is the following spectroscopy methods does not involve the interaction of organic molecules with electromagnetic radiation. Mass spec is the only one that doesn't involve um, irradiation, right? Because NMR, infrared, obviously infrared, UV spectroscopy, UV, um, and nuclear does radio waves, right? So that's it for this part. We did the questions. Hopefully you stuck around. If you didn't, do them yourself. And if you have any questions, come back and see the explanations. So right now, we're gonna go over the summary. So NMR R spec. Okay, so first things first, we have HNMR, right? And then 13CNMR. This splits? No, splits, right? So get that out of the way. And we said NMR is caused by radio waves. We use radio waves in NMR. So we mentioned that earlier. Oh, let's see here. Okay, so no splits, radio waves, things like that. And kind of just a little bit background with NMR is that we use, this is gonna be kind of physics. Well, it is physics. So we look at magnetic wave, the electric field, and then the wavelength and things like that. So just kind of like, that's what you should be imagining. And this causes, with all the and you'll, once you get to OChem2 and then you go to physics, or even vice versa, you remember where all the poles flip, right? Because of magnetism or whatever, right? So causes nuclear spins to flip. So something like this can turn into like that or something, right? So it makes it flip. It doesn't break it, it doesn't excite it, right? It just flips them. So now the electron environment determines, of course, the size of the magnetic field. So that's a good concept question, because the things that are getting affected is the magnetic field. So each different functional group, each different bond, each different strength, each different electronegativity affects that magnetic field, right? So that's kind of what they're talking about, and it's very sensitive. So if you end up with an odd mass, you know, you'll have one of these, and you won't see these used in OChem, um, but they're just kind of there to, you know, these are what you use in NMR to radiate it type thing. So you kind of see here HNMR, we use H1. For CNMRs, we use 13. So there's also fluorine NMRs and then phosphorus, things like that. So odd atomic number, also meaning we have 2H, 14N. So these are just the types of NMRs, right? No big deal. Okay, so now the good stuff. MR spec. So we have the graph, right? Intensity goes over here, and chemical shift, which is the ppm, goes over here, right? Goes over here. So what's at zero? We always have one here at zero, and we know that's the standard, the TMS. So that's kind of like setting it up, like TMS is zero. So, okay, and we know upfield, shielded, downfield, deshielded. And also, just more information, the more you go this way, decreases the magnetic field, which is denoted by B. and increases frequency, right? And then vice versa, right? So you may or may not need to know that depending on how physically, like physics wise, right, inclined your professor is, if they want to get into all of this detail. Um, that sucks, but you know, that's what it is. That's how it is. So chemical shift, so that's interesting, right? So now we go into the spin splitting. So this is where we um, talk about coupling constants, coupling constants, and which just means frequency difference. And this is where the m1 times n plus 1, things like that come in. Okay, and then just to kind of put a spin splitting. Oh my gosh. Okay, non-equivalent protons, right? So AKA environments, AKA environments, right? So now we have n plus 1, which is splitting um, when only one adjacent carbon that's different, right? Different. One different. One different, right? So n plus 1, m plus 1 equals splitting when two different adjacent carbon, and I guess environment, right? Let's make it specific. Environment. So, and we know n equals number of hydrogens in that environment, right? So, oh, I guess one more thing. OH equals singlet, right? So that's another box, I guess. Right. So nothing too crazy. With that being said, that's it, right? That's like one chapter summarized into two small pages. Um, and again, you'll have the charts to kind of know where the chemical shifts are. Depending on your professor, you may have to memorize it, or you may have the chart with you on your exams, right? But as long as you know which ones are being deshielded, and again, the concept of electronegativity, who's pulling away, who's pulling what from you, right? So that's all I have for you this video. Hopefully it helped. And hopefully you come back and watch the other videos. And for OChem 2, it'll just get more interesting, I should say. Okay, so that's it. All I have. Thank you guys for watching. I'll see you guys later. Bye.